Good afternoon, everyone. Welcome to today's research seminar. It's a pleasure to introduce our guest speaker, Dr. Osiris Valdez Banda, Assistant Professor at Aalto University. Dr. Banda is an expert in maritime safety engineering and leads the Safe and Efficient Marine and Ship Systems Group. Today, he'll share insights on safety assurance in smart maritime technologies and concepts with a focus on risk analysis, autonomous ships, and regulatory implications. So thank you for coming, and we are very glad to give the floor to you. Please join me in welcoming Dr. Banda.
Thank you very much, Crystal, for the introduction. So today I have prepared this presentation for the seminar where I try to discuss kind of like critical elements we have experience on our research related to how to ensure safety on the design and implementation of smart technologies and concepts. So I will have the presentation will be in a way that I will introduce myself and my research group quite quickly. And then I will show basically the developments related to this topic into specific projects that we have closed recently. So if we move forward, then let's move with the introductions. So I think you know I'm coming from Aalto University. Basically, I belong to the School of Engineering, Department of Energy and Mechanical Engineering, but inside of the department, we have this Aalto Marine and Arctic Technology. So that's you can see on the screen, the different kind of research area that we have inside Marine and Arctic Technology. We have the ice mechanics and Arctic marine technology on the upper right part with the three professors there, Mikko Suominen, Jukka Tukkuri, Arto Polojärvi. And then we have Otto Pollaka, which is our lab manager in charge of everything related to research and testing on our ice and wave tank at Aalto. So then below, we have the marine fluid mechanics and operations. We have a part-time professor, Teemu Manterbakka, and our lecturer, Tommi Mikkola. Then in the lower part on the left, we have marine structures and sustainable production with Professor Romanov and Professor Heikki Remes, which is Heikki is now our marine and Arctic technology leader. And then in the upper left corner, we have a kind of we can still call it a new group, which is this recent intelligence in marine systems. We are two professors there, Mashura Musharraf, working on intelligent systems and the human-machine teaming. And then myself working more in things related with risk analysis and safety assurance. So inside of this kind of research clusters of marine and Arctic technology, we have our own research group, which I want to show quite quickly. But before, just to mention about my whole path to basically coming to Aalto, where I am now as an assistant professor. I graduated from industrial engineering in Mexico long time ago, as you can see it there. Then I immediately joined departments related to quality and environmental management in the petrochemical sector, but mainly the petrochemical sector also linked to port logistics. That's basically where I worked for almost 4 years there. Then I moved to Spain, where I did my master's degree in quality and environmental management. I worked for a while for the Port Authority of Valencia, then before moving finally to Finland, where I joined the European Chemical Agency in 2010 for a short period, before at the end deciding studying a new master's degree in industrial engineering and service management at Aalto. But then at the time I was doing that master studies, then I joined marine technology at that time at Aalto for doing my master thesis, and then connected to research, basically working as a research assistant in one project related to safety of the Finnish maritime cluster. And then since then, basically, my whole path started from research assistant, doctoral candidate, postdoc, I went a while for a visit, a research visit to TU Delft, and then I came back and I became assistant professor in 2020. That's basically my whole path there. So what I do as a professor together with my group, so our research focuses on the elaboration of scientific methods, models, principles, and tools for goal risk-based design and operation. Particularly, this focus, we analyze it in the context of smart shipping, winter navigation operations, maritime traffic risk analysis, and also accidental oil spill prevention and response. That's some kind of like a context that we had heavily worked on our group. Nowadays, we also have projects related to resilience of port infrastructure. So basically, the scope of where we apply these new methods and new principles for goal risk-based design and operation is something that we are basically doing. Then why is so that the scope is extending is basically we look the ship as a main focus on a specific kind of like how we call it here, maritime ecosystem. So we look into having this system understanding where we look into systems that are on board the ship and then systems who allow the ship to be efficient and safe in operations. And this basically relates to systems that can be located in fairways or systems that can be located in ports or everything what basically enables the ships operate in a safe and efficient manner. So having this focus, we do this risk and safety analysis to basically determine alternatives for generating new management strategies for risk and safety. And of course, one of the main aspects there is to prevent accidents and response to those. We try to understand how our risk and safety work contributes to the development of a sustainable ecosystem. So how it basically links society, economical use for ensuring operations in maritime shipping. And then, of course, what is the kind of like a technical development that we can support with our new models. So we try to align always what how safety and reliability combine to have an efficient and reliable design and operation of these systems. And then what aim that we have is also how to determine elements to make our systems ready to any kind of like a event that they may face, and then having at the end kind of like how we can call it resilient systems on board ships or in the maritime context in general. So this is basically the scope of our research that we do in the thematic that we cover. And in order to make it more concrete, I will show you these two research projects that I will present today. Quickly about my research group, I'm not going to stop in all of them because I'm a little bit concerned about if we will have enough time to go through the whole presentation, but you can see there. At this moment, I have two postdoctoral researchers there, and then 4 full-time doctoral students working in, for example, data analytics for analyzing risk in maritime traffic, analyzing risks on this kind of like a new green strategy for the Finnish maritime cluster, analyzing risks of ship operating in ice conditions. And then, as I mentioned, we have this new topic on resilience maritime ports and fairways. So that's something that we are doing there with 4 doctoral students. Then I have 6 part-time doctoral students, which are basically, these are people who are working, and part-time they basically do research also connected with the aims and the thematic dimension. I have people working on the development of maritime autonomous surface ships technologies and system resilience. I have another part-time doctoral student in oil pollution preparedness and response risk management. Then another student working on the developing of the traffic emission models. Then goal-based risk governance for smart shipping and risk informed planning for the future of BTS. And then pilotage operations in intelligent fairways. So are some of the topics of my part-time doctoral students. Then people who already graduate from our group. So these are people that graduated in the last in 4 years at least. Dule graduates on provide his doctoral thesis on maritime traffic risk analysis in Northern Baltic Sea, utilizing AIS data. Then Sunil graduates on the analysis and management of risk in maritime remote pilotage operations using the basis of the formal safety assessment. And then Miriam graduates on advancing safety in autonomous shipping through modern hazard analysis methods. So that was the titles of their doctoral thesis. And today, related to Sunil's and Miriam's thesis, we will look into specific developments on the projects that basically that they work on this thematic. So, but if we go to the context of smart shipping, particularly many people, when we talk about smart shipping, they immediately correlate the smart shipping concept with the focus on autonomous ships. But we will see that actually it goes beyond that. But autonomous ship is something that is quite important for the concept of smart shipping. It's something that is giving a lot of kind of like opportunities for transforming the maritime cluster and then trying to see what kind of alternatives we can develop on executing good collaboration between new technologies and people with expertise on the maritime world to basically allow our future maritime operations becoming smarter, safer, and greener, of course. So, but if we basically look into how we can understand an autonomous ship or how these maritime autonomous surface ships are defined, by, for example, by IMO. IMO is basically mentioning that the autonomous ship refers to a ship which, with a varying degree, can operate independently of human interaction. So they basically consider that an autonomous ship has they call it here disruptive potential with implications in terms of technical, economic, environmental, legislative, and social impacts in the years to come. So that's something that is expected that the whole transformation will be generated by introducing this new type of vessels. And of course, if we basically manage to organize everything what is needed to make autonomous ship in the future efficient, safe, and aligned to the purpose of improving also the environmental protection and the safety of shipping in general in the future, we can expect that this type of ships should improve significantly the logistics, the safety, and of course the overall environmental impact of the maritime transport. So that's kind of like the expectation, but it's not easy to do it. So we need to do a lot of work before actually we can start to see how these concepts or technologies embedded into smart ships are safe by design, which is a quite important element to determine now. So in reality, what is the big challenge here for smart shipping is that we still need to have this ecosystem perspective as fast as I briefly defined it before. And this is basically quite important because it is clear that an efficient operation of any intelligent ship or autonomous ship will require for us to establish an intelligent environment. So that's something that it's not going to work if we are not allowing to make our operational context also intelligent and ready for this type of systems to operate in an efficient manner. So, and that gives us a huge challenge because when we talk about this smart ecosystem concept, we need to understand that we don't cover only those technologies on board the vessels, but also the design of technologies in ports or waterways, so that the whole kind of like a logistic change can basically be transformed in a fully smart kind of like a concept. So the assembling of this ecosystem and this transformation and the introduction of these new technologies is basically generating a transformation of the maritime cluster in general to become more multidisciplinary. So new kind of like a expertise and new kind of like professionals are joining also the maritime cluster, particularly in elements related to artificial intelligence and the development of those technologies which will align or will allow to have these intelligent systems operating in the future. This is the main transformation or the main kind of like introduction of expertise for the cluster. And of course, this ecosystem assembly requires the involvement of the current maritime stakeholders and the involvement of new experts like the ones I mentioned already, automation, robotics, AI, etc. So the challenge is there. It's quite important to understand and to see. And we will see basically what had happened actually in autonomous shipping. I will basically make this short summary at the beginning, just in relation to projects where I have been involved. I will mention some other kind of like projects that now they are going on in different areas, in different countries, and what they are doing. But I want to keep it short for the discussions today. But what I can see from the last 10 years where I have been involved in research related to autonomous shipping is that we start this kind of efforts to think about these smart ships, these autonomous ships operating in the future maritime cluster many years ago. I think if I go back in time, we started this kind of like development of ideas, and then finally generating the first projects in 2016 with the Advanced Autonomous Waterway Applications Initiative. It was basically a project to start to test the context and the cluster, not only maritime, but the cluster of technologies in Finland, which can basically be working together in the future to allow this transformation and to allow to start creating some kind of like a new technologies and new kind of like a chip concepts and the entire constitution of what we call it now, this autonomous maritime ecosystem. So it was about discussing with the industrial cluster, discussing about the potential alternatives to develop concepts and ideas for the future of the maritime cluster, which basically then this type of like an initial project opens new project applications related to more specific case studies, like for example, remote controlled vessels, autonomous ships concept, the development of autonomous navigation systems in our project Design for Value in 2017, which basically was a very large project. The whole, I will say, and I'm sure I hope I'm not mistaken, but I'm sure that the whole maritime cluster in Finland was basically on board of this project in 2017, when we started to discuss with the main maritime big companies leading this transformation to start to think about alternatives on the development of technologies, the constitution of, for example, remote control centers and technologies on those areas or on those centers to allow this smart shipping. And then, of course, we start to talk about how we can ensure safety and what are the elements that we need to basically focus on the assurance on safety on the early design phase, where we need to determine all type of technology that can be implemented to that. So it was a large project that then basically opened to smaller projects, we can call it that way. We work on projects related to autonomous ferries operating in urban waterways. So we evaluate some specific concepts for application, for example, in the city of Turku in Finland, where the small vessel basically executes autonomous operations in a determined context for moving people safely from one area to another. I think the city of Turku basically has the results of the evaluation, and they are basically moving these ideas forward on developments. Then after Design for Value, we look into specific applications of smart shipping, and then we create the C for Value project, which focus on remote pilotage operations. I'm not going to say much about remote pilotage because it's one of the projects that we will go into details on this presentation. But that's basically something that we start in 2020. We start to elaborate all the bases that we need to allow the provision of a service that gives this pilotage from a remote location. Then, of course, at the university level, we identified that all these changes coming from this autonomous shipping or this smart shipping will require to basically update the professional profiles of people, basically carry on tasks in the industrial domain. So we start to look into how to evaluate the changes needed for example, for the educational programs of maritime professional that we have in Finland, not only at Aalto University, but I think the entire a cluster of universities linked to the maritime domain were basically working together to see what kind of changes are needed for the next 20 years in terms of the education for professionals related to maritime education in general. Then another project that I'm going to be presenting more in details today is the ECAMARIS. We started in 2022. 2022, if I remember correctly, we closed it actually last year, which basically we work with an industrial partner for analyzing some specific technologies that will allow to have a specific ship intelligent concepts that we will revise in details quite soon. And then finally, a project where we look more into combination of autonomous shipping, the Green Deal, and then challenge that we have, for example, in Finland related to navigation in ice conditions. We start to analyze kind of like a recent opportunities from the digital solutions in this kind of like a strategy or this transition that we go towards having this carbon neutral marine logistics and a smarter kind of like a performance of ships.
Who is funding this Kudosko? Who is the funder?
Academy of Finland.
Okay.
Yes, this is Academy of Finland. Yeah, Academy of Finland is Gyroscope. ECAMARIS was Business Finland. Aalto was the Ministry of Culture and Education. C4Value was Business Finland. Then Smart City Fairs was the European regional funding. Then Design for Value Business Finland, and I think ABA was also Business Finland, if I remember correctly. Yeah. That this is happening not only in topics related to Finland, but you can see other countries are doing efforts related to these autonomous ships and this type of technologies in different kind of like projects and cases, at least on this country that I have basically below. We can talk more about those then later if you want. So smart shipping safety assurance. So we require to have, like I think I repeated now 3 times, this kind of like a systemic perspective, looking to the entire like a constitution of the maritime ecosystem. If we want to call it the like autonomous maritime ecosystem. So, and basically this is needed because for having this safety assurance, all these smart ships demand understanding of the functioning of the entire ecosystem. And we require the incorporation of multiple viewpoints. So an interpretation for that. So also we need to see what kind of is the reception for this smart shipping from different kind of like clusters in the maritime domain. And sometimes we can see that this reception changed depending on the type of cluster or the group of experts that you are trying to talk about this new transformation. And of course, when we think about what is the purpose or what can be the benefit for introducing autonomous ships, so autonomous ships or smart ships in general. So we know that the smart shipping has to be somehow suitable for increasing the competitiveness of the maritime transport stakeholders. So it has to be a clear benefit for the business side, environmental impact or efficiency of operation. That's something that has to be always represented there. And of course, which is more relevant for this talk today, the concept of smart shipping, whatever it is either a technology on board or it's either an entire new ship concept or something embedded into the fairways of operation on ports. We know that it has to be safe, reliable, or resilient if we can also make it that way, and sustainable. So that's kind of like a mandatory for the development on that. I was talking with the colleagues this morning about that, especially people with expertise on robotics, AI, they always claim or they always say that in the maritime cluster, we are very difficult people. Everything is difficult in maritime. Another thing that is that we are difficult people, but the entire cluster is kind of like a quite big. And it's important to understand that the complexity comes by all the stakeholders that you need to get involved into making this kind of transformation. So we think about this inter and multidisciplinary collaboration because when we look into maritime stakeholders, and I will just quickly punch buttons here, we can see there is a huge list of people that need to be involved in the transformation. So this transformation cannot be just done by specific groups or specific type of expertise. You need them to have the entire maritime cluster embedded into the development of solutions. Otherwise, what we develop for the future then is not going to work. So that's why then sometimes making this kind of like a elaboration or design and implementation of these new concepts is more difficult than in other, for example, industrial transport domains. That's how it is. It's just the nature of a maritime cluster. We need to have this sustainable competitiveness there. So if we look into the common kind of like I call it here promises on smart shipping, is that it will allow to create a concept which are more competitive due to the increased efficiency this is basically given by the reduced operating costs and improved environmental performance. So that's kind of like the main kind of like a promise embedded into this smart shipping concepts. So what exactly or how exactly is this kind of like a sustainable competitiveness represented? We can generate optimized routes, the speeds and fuel consumption in a more controlled and smarter way. And this will lead to a lower operating expenses and an enhanced environmental sustainability. So it's also mentioned that this smart ship concept or autonomous ships, however you want to call it, will enhance operational flexibility and potentially will reduce accidents caused by human error. And I mark that in red because I don't really like that definition in general. Because also many of the affected operations we have nowadays in any kind of like a sea area happens because of humans. So humans are not just the ones to blame for the potential errors and issues that we may have, but they also provide a kind of like they are a critical element into defining an efficient and safe operation of ships worldwide. So we need to have the humans in the loop all the time, and this is something that we will show in the example of the project that we have. That it's not about replacing humans; it's about supporting humans with enhanced technologies, and humans will be always in the loop of autonomous ships or smart shipping concepts. Then we have different kind of like elements to push forward the idea of how we are moving towards this definition of new technologies or new ship concepts. I think many of you may be familiar with this IMO scoping exercise to determine the 4 degrees of autonomy, which goes with autonomy 1, shipped with automated processes and decision support. Automated and autonomous are somehow differently, and we will basically review the differences quite soon. And then, of course, the degree 2 is basically covering these remote controlled ships with seafarers on board. Degree 3 is remote controlled ship without seafarers on board, and then the final level 4, is a fully autonomous ship. But of course, this is kind of like in a general way of understanding how we can understand these autonomous levels. But we know that some of these technologies may be drifting in the application from autonomous level 1 to 2 and 3, depending on how they do it. So there are other categorizations on these autonomous levels. You can see some of the classification societies provided their own description for these autonomous levels, but then I basically choose this one from one white paper from 1C ecosystem, where defined 6 different levels, started from level 0 with the basic operation, then level 1, which is basically assisted operations. Basically, they call it hands-on, eyes-on, mind-on. Then the level 2, which is basically partial automation with hands-off at the times, and then eyes-on, mind-on. Then the level 3, conditional automation. Then level 4, high automation, and then level 5, fully autonomous. So I think in the cases of the projects that I will present today, I put this autonomous level representation because we will see applications mainly into level 1 and level 2. That's basically where we are now working, or we work on these projects. And then, of course, another big challenge, and that's basically where a lot of people are making huge work, is on basically try to see the impact on the regulatory framework by the introduction of this new like a smart ship concept of autonomous ships. So there are many conventions that still don't consider or cannot basically foresee the incorporation of these autonomous technologies and concepts. You can see some of the examples I have there in the screen. I'm not going into these details, but this is something that at the end, there is a group of experts trying to evaluate how these specific regulations, like, for example, coal regs, the HTCW, and in general, everything what is embedded in SOLAS can basically adopt potentially the purpose of these maritime autonomous surface ship technologies. Of course, there is the development of the MAS code, which is ongoing, where the first kind of like a deadline for having it ready, I think they say was first 2026, but I think now the updates are moving the definition of that code by 2028, if I'm correct. So there is a lot of heavy work going on the development of this MAS code and affectations to the regulatory framework. So many challenges, as you can see, many things to be incorporated there. But then we start to look into specific study cases that we have for smart shipping safety assurance. I will start with our ECAMARIS project, our enables and concept for autonomous maritime solutions. This was a project that we basically developed with different partners. ABB was together with VTT, were the leading partners in Finland for the pushing of the project. Aalto University in robotics, AI Live Sim were other kind of like a partners involved there. And this project particularly focused on having this development of maritime autonomous ship system technology. So specifically one technology, which we call it the electronic lookout. The concept for the electronic lookout, you can see it in the picture here. So basically we had the data line on site, which kind of like a recognition from cameras and sensors can basically understand or basically represent what our ships are facing when navigating. And this will basically will be provided information for electronic lookout with the support of some kind of like a AI agents for understanding how to identify and detect and identify the specific elements on the operational environment to support the role of the bridge team, particularly the officers of the watch. So basically, we start to think about the utilization of this type of technology and this electronic lookout concept. And we focus on evaluating first 3 use cases. The first use case was the relocation of the bridge with the support of the technology that I mentioned. So that basically make possible to safely relocate the ship bridge to a position with limited or not direct visibility because it's going to be supported by the electronic lookout. Then another concept that we basically consider for the utilization of this technology was the conditionally and periodically less manned bridge. So basically having less people on board, less people interacting on the bridge, or sometimes even leaving the bridge unattended and supported by technology. It was something that we considered there. And then something that we considered but we didn't develop too much in the was the bridge shielded concept. So basically not having a bridge as such and just having the support of the operation, but we didn't went too deep into the application. We focus more on these 2 initial cases there. So, but with these 2 cases, we start to look into what kind of tasks we will develop as a basis for start to introduce this type of technologies. And then we start to basically create things from the scratch just for that technology, just for the application of that technology in a specific context. You know, we knew the type of vessel that we are going to evaluate. We knew the route that the vessel will be operating. And then from there, we start to determine how to basically utilize this technology. But the first thing that we developed there as a task was basically the development of the concept of operations. So having a CONOPS that determine basically how the technology will be operating, particularly how this human-machine teaming will be basically established. As I said, in this market here, humans will be always part of the autonomous system, and that's why it's critical to decide which function will be allocated to humans, which ones to machines, and how basically you can assemble this human-machine teaming. So that basically with this human-machine teaming, we can determine the functional requirements, the functional allocation, minimum technical requirements. Of course, also we focus on safety requirements for that. And then to represent what is the kind of like a technology, technical capability for executing the operation that we planned on the concept that we basically introduced. And then another critical task for us in the project was to describe functional and safety requirements. So describing the functionality of autonomous technologies. So representing this kind of functionality and the meaning of automated levels in of the technologies with a kind of like a risk goal-based approach, particularly on this kind of like a determination of the level of autonomy. We also identified that technology and those potential concepts and the functionality of that technology will be basically moving from different autonomous levels depending on the operational context the ship is facing. So that was important to understand that the capabilities of the technology that we have at that time, it will be just optimal if some requirements for the operational context are fulfilled. No, but as I say, we went really to the scratch of everything what we tried to do. So the first challenge that we noticed is that for developing these concepts, this concept of operation, they were very kind of like a limited guidelines to basically establish a way or a process for defining our concepts, these technologies. So we went one step back to define a kind of like a new process for determining our concepts. And we basically produce this kind of like we call it the Icamaris concepts template, which is designed to provide a kind of like a framework and guidelines to support early and compressing identification and collation of key information assumptions about systems and its operational context. And we basically determine that this context, basically, or this template will support the description of system interaction with industrial main elements and operations. And we can utilize it, for example, for ships, ship systems, for remote control centers. We basically also include this pilotage and remote pilotage as a concept to be included also with the development of this or with the utilization of this template. And of course, it can be utilized for other maritime infrastructure, for example, defining new technologies for aids to navigation in fairways and ports. Better support operations, like, for example, things related to new embedded elements in BTS. And SAR services, for example, and TUC assistance, that's something that we can think, or we believe it can also be utilized with this template. But then once we have the template, we start to utilize it for our actually electronic lookout system purpose. For time restrictions and for all the information I can present to you, I will just basically go into the general elements of what we developed for this electronic lookout. For publications about this work are basically online. I can share with you then the links where you can find more details about what it was produced as a CONOPS for the electronic lookout. Also, some papers are still, some scientific papers are coming on this topic. And but I would show you just here the general kind of like a template for all the general description of the CONOPS that we put for the electronic lookout. So we look into these two potential configurations for the bridge team. So with basically having the minimum permitted bridge team with the officer of the watch, normal lookout and the electronic lookout working together. So kind of like supporting the technology for the role of the officer of the watch. And then what we call here the small bridge team consisting of the officer of the watch and only the kind of like electronic lookout support. So a little bit more advanced combination of these roles of person supported by the use of the technology. We need to determine, as I say, when actually the technology can be utilized. There are still limitations in specific, for example, weather or environmental conditions where the technology still requires some kind of like new elements to be 100% considered as a potential solution. So then we limit these kind of like conditions to open sea passage, voyage phase with good weather conditions and account sea state. So that's basically the utilization of our operation at the project as we describe it here. So what were the functions for the detection of external objects? So what kind of like Objects it's supposed to detect and identify where things related to ships, boat, shipwrecks, debris, shipwrecked persons, other navigational hazards related to infrastructure, any kind of floating objects, buoys, safety marks, other ship lights, and also distress signals are something that it was basically part of the recognition of the functionality of the e-lookout. Land, we talk about ice, irrespective of the shape and form, and then sandbanks or prominent navigational features that we can actually identify there. So some of them were just about detecting, some were just about detecting, but the identification then it was particularly focused on those who can be easily identify and recognize and by the technology. So with that, we basically start to have a detailed description of the functions of the electronic lookout and human automation teaming, as we call it here. So we have several functions, and I will try to basically show this quite quickly. We show, for example, the first function, number 1. It says that the e-lookout should continually detect and discriminate between objects of interest, for example, navigation and safety-related objects in the bathroom. And basically, we determine the level of automation by combining a specific stage, either the technology is sensing, perceiving, making, sense-making, projection, planning, decision-making in act. But particularly for the project and for the autonomous levels that I mentioned already, we just focus on defining the functionality of this e-lookout on the sensing and perception state. So, and we define that, for example, in this initial function number 1, it's going to be basically making the sensing in a fully automated level. But then when we go to function 2, when it's about recognizing and assigning to a class objects of interest on surface relevant to navigation and safety in accordance with the distance defined in call regs, some analysis of specific rules on call regs, we basically determine that this function will basically be doing the sensing and also the perception, but it can go into the kind of like a 3 type of levels going to from manual to fully automated applications, as we can see it. It's like a table described there. So we do this for all kind of like a functions that we detect there. This here are only 5 examples, but I think there are more than if I remember correctly, more than 15 critical functions that we identified on that. And that's something that you can find in a more detailed document that is available there. I will share with you that. These links then later on this presentation. But basically, with this functionality on describing how the lookout should operate and what are the kind of like functionality will have with what kind of level of automation each functionality will have, we start to define what are the capabilities of this kind of like technology in order to efficiently define how that technology will be collaborating with the people on the bridge, and how the technology can be implemented specifically into the 2 concepts that we evaluate, this periodically unattended bridge, and then this relocation of the bridge, as I already mentioned up there. Then, of course, we look into having these functional and safety requirements. Particularly, we got very good support from experts on knowing how to bring this type of discussion and this type of changes to the IMO level. So we define a process where we basically put goal-based standard processes for identifying the key enabled technologies and the goals for that on our electronic lookout, and then defining minimal functional requirements related to the operation of the electronic lookout, how this operation can be basically verified and evaluate how the conformity of that verification will fulfill the specific regulations that are relevant for the electronic lookout. And then, of course, how to basically determine industrial practices and standards for recommending some changes and introduction of this type of technologies. So, and then for these techniques that we utilize for the whole process, as you can see it there. So basically, there is a kind of like understanding the high-level functionality of the electronic lookout, and then having this breakdown of the functionality, making a risk assessment for the whole e-lookout system, determining risk control measures for the issues that we identify in our risk assessment, then cross-check our results from the risk assessment with the relevant rules and regulations, and then the development of novel rules or new kind of like changes in rules required for the introduction of those technologies is something that we evaluate there. And then the identification of relevant standards and potential requirement that will be needed for the introduction of that type of technology. For that, we recently published a paper on having this entire definition for the electronic lookout and how to basically make the whole processes to bring it to introducing changes for defining this autonomous shipping requirement. The link is there. I suppose that later then people can have this presentation and then you can see in details all the study that we did for that. But that basically is something that for these requirements, we specified the sector criteria for our concept. So in the view of high uncertainty, we basically have this focus on just critical accidents that we need to be basically preventing and basically avoiding in terms of having that know the technology cannot lead to this type of accidents, like for example collisions. Grounded were some of these accidents mentioned there. And then, of course, we use this ALAR approach, as low as reasonable possible or low as reasonable achievable in this case, for defining how these kind of like technologies should basically control and mitigate the risk that you can have there. As I say, we always do this in alignment to the current regulations and rules. We can see, I will show quickly a very ugly table on all the hard work that we did, just for you to know what kind of like a definition of risk and risk control options we have and how we identify that it's a link strongly to specific regulations. Of course, we try to go beyond just preventing and responding to accidents, particularly because we see the capability of autonomous ships to go into more advanced practices for safety, like, for example, also learning new or strengthening the capabilities of the system to always enhance the safety performance. So we try to do some kind of like a critical solutions for having these elements to allow our system to be resilient, to be prepared for any case that the system may face and not collapsing. So it's more challenging. So we try to look into this. Ethical alignment or ethical evaluation or ethical equivalence, as it's called here. So what is the ethical principle that the system need to be determined there? That's something that was also documented. Interaction with the external stakeholders that can be affected by the utilization of the system. Different risk levels for different stakeholders were determined. Context-dependent requirements, as I said, we were quite specific to know how the functionality is influenced by the determined context where the technology is operating. That's something that we evaluate there. And this is what I say about the ugly tables. So this is just to summarize all the hard work that we have on this and all the definitions. We have a total of 7 functional requirements and then 17 RAMs for this reliability, safety, maintenance, and adaptability of our system. And basically, we determine those functions there with a specific kind of like a label. Then we identify requirements that will need to be fulfilled and what was the main source for these requirements coming from the specific regulation that we analyzed. So some examples that you can see there, call regs, STCW, and some other kind of like design rules were also included there. Then these specific RAMs requirements, we defined it there. So 17, so some examples you can see there, like for example, assuring that the functionality of the e-lookout in all environmental conditions in the operating environment should be ensured. Shear movements, temperature, humidity, illumination, vibration, some specifications were basically included there on this type of specification. If my battery is dying, so I will connect my computer quite fast.
Give you my charger. You have some.
It may work also, yes. Hopefully. Yes. Sorry for the pause here. But yes, as I say, that's a lot of heavy work done. It's almost impossible to show all details on this presentation, but I basically recommend you to go into the links publications that we have so you can see more details about all the work. All these kind of like tables related to our risk assessment, functionality or function that we are evaluating, the hazard that we identified, how deep we went into the description of the hazards that we identified there, the phase of the operation of that electronic lookout, the specification of the operational conditions for this kind of like applicability on the specific phase that we evaluate, the effects the hazard may have, consequences, and then try to basically make an assessment or classification of how severe or significant the hazard may be for the operation of the electronic lookout in this huge table that we have there. So there was a lot of things that we found. Some of these things were basically immediately linked to a specific risk control option. But of course, there are limitations on utilizing those risk control options. We need to make sure that the control options will be properly adapted to understand how the system should operate when we have all the needed context available or ready for try to basically, how can I say it, like try to basically confirm that we have all the optimal conditions for having the most efficient utilization of our electronic lookout. So all details were basically analyzed there. So in conclusion, for this electronic lookout, the e-lookout, the development focus on its application for a specific ship conceptual operation. When I say ship conceptual operation, we basically evaluate a specific carrier, a small container carrier. That was our main kind of like a case of evaluation. And the route that basically we were evaluating for this ship was basically navigating between Helsinki and Travemünde in Germany. That's basically something that we evaluate as an operational context. The development of the work focus on the basis for defining a coherent and what we can call it an initial solid CONOPS, something that we can basically build on. So identifying how for that context, for that ship, the electronic lookout may be efficiently, and then potentially elaborating more elements for future development of the concepts or the other kind of like a case studies that we want to utilize the electronic lookout in the future. Like, for example, this zero breach concept is something that we are discussing for potential future developments in the upcoming year. Then it says here the functionality of the lookout is now determining a specific team configurations and operational conditions. As I said, it just gives the basis for future development. Functional and safety requirements are now produced as a basis to consider the technology's approval and applicability to determine operational cases and conditions. So these kind of like requirements and this kind of like research and evaluation that we did actually were presented in different groups. Some of them at IMO level, some of them at European level. So we were basically presenting what is the potential application that we can have in the electronic lookout for practical implementation in the future. And the work will continue with the development of technology in the context of other operational contexts, as I say already, like this. Continue with this periodically unattended breach and also the breach zero concept. So, but that was about the electronic lookout. Then I will jump into C4value and focus on remote pilotage operations. So remote pilotage or C4value fairway program was a very long project. Basically, you can see all the partners involved in that project. The funding instrument was Business Finland, but basically the main idea was here to establish the basis for generating a new service that allowed this remote pilotage provision in specific fairways in Finland. So the idea here is that to work hard towards having this type of service ready in the upcoming 5 years. That's a little bit the target that we have. There are new initiatives that we are working on developing the continuation of the work that you will see here. So, but let's make clear about what remote pilotage actually means for our concepts. So it mentioned here that instead of pilots boarding to the ship, in remote pilotage, the remote pilot will support the ship crew remotely from a shore control center. So it's not a remote pilotage controller, it's just the provision of assistance from a remote location, so that the pilot is in a remote location and with the instrumentation of having an intelligent fairway and everything what the ships which are maybe selected for the provision of this service can be incorporated into this joint of technology to the pilot basically provide instructions and allow to have this remote pilot service without the need of the pilot going on board. So it's not remote controlled. That's something I want to make it quite clear because some people tend to believe that when we talk about remote pilotage, people are basically taking control from a remote location, at least not in this case. Of course, we are thinking about potential developments. This is something that still is on discussions or kind of like a potential new application in the future, but that's not the main kind of like a focus that we have on this project at this time. So in order to basically start to think about this remote pilot service, we also need to basically look into what the Pilotage Act in Finland specified on the provision of pilotage. So the Pilotage Act was amended in 2019 and then again in 2023. And for 2023, we need to do kind of like a detailed risk analysis of critical fairways in Finland together with authorities was involved in that work. And we basically evaluate the type of risk on these critical fairways and thinking about what are the possible optimal fairways for the provision of this remote pilotage. So unfortunately, about this risk assessment that we did for critical fairways in Finland, it's not information that is publicly available because it's basically with the maritime authorities there. But this is something that we did inside of trying to understand clearly the risks that we have on critical fairways and then to think about what is going to be the main challenge when we focus on the provision of remote pilotage in the future. There are some additional challenges on this remote pilotage concept. So we have more software and new advanced technologies. So more embedded software and new advanced technologies are prone to software and design errors. So this is quite important, and that's something that we will see through the full presentation, is that one of the main challenges for the maritime domain here is that when we are creating these new systems, we need to make sure that these systems are safe by design. So the entire cluster will need to invest more efforts and resources for making these systems ready at the early design phase or safe at the early design phase. This is something that is quite important because as many of these are basically intelligent technologies or technologies to be incorporated there, making corrections afterwards, what we see on the application, it will be quite difficult and quite costly in a way. So that's something that is important to understand, that this transformation has to be done at the early design phase with the highest compromise for incrementing resources from the maritime cluster. We will have higher number of interaction between components. So this can result into unsafe interactions. So this type of interaction, we need to really evaluate how we understand the behavior of our systems and the interaction between components that we have in the system. It's quite important to know how to evaluate this type of issues. Then we need to check requirements, what we are allowed to do, as I say. So we will need to focus, particularly for our case, how the Pilotage Act specifies that a comprehensive risk management study is necessary to enable this remote pilot service in Finland. And this is something that we start in this project, and we are trying to continue now in a new application that hopefully we will get news about this potential new project in the upcoming months on this remote pilotage. But for this starting this risk analysis of remote pilotage, we basically utilize a systematic approach, which is quite familiar to many maritime experts, which is the formal safety assessment, which focus on these 5 steps that you can see on the right. So we need to develop a description of the system to understand what are the system components, how it works, or how it functions. So this system composition was very important. Then in step 2 and 3 and 4, we need to conduct this kind of like a risk assessment and generate kind of like options risk control options to manage the risk of remote pilotage. So then we basically integrate for this kind of like a risk analysis, we integrate different type of methods, kind of like a novel methods for executing each step of the formal safety assessment. And then finally try to determine a solid basis for a management strategy, defining roles and responsibilities and documented for remote pilotage. So that's basically something that we followed in the process for our risk analysis. But of course, one of the biggest challenges on this FSA was having this system description, defining the goal, scope, and system definition. As the formal safety assessment has limited, basically, guidelines to know how to define this system, we need to look for more advanced alternatives, which allow to define systems that also allow to use models to define our system that support the elaboration of the technology as such, and then the analysis that we basically need to include on the evaluation of the design of this technology, like, for example, analyzing risk and determining safety aspects for that. So with this limitation, we start to look into new alternatives. Particularly, we look into this model-based systems engineering. We look that this is kind of like an approach that helps to reduce this ambiguity or this lack of support from specifications in the formal safety assessment with the use of models and kind of like a minimizing text description to go more into alignment and connection of all components and models and functionality and calculation that we can do for the functionality of such systems. This is not easy to adopt because basically we just realized that in this model-based systems engineering, there were different methods available for doing it. So we need to first define together with end users, together with the people who are basically designing or will operate this kind of like a technologies embedded into the remote pilotage concept. We start to test with them different alternatives. I think we test around 3 options for model-based engineering. And then we test common approaches utilized for risk analysis, like, for example, utilizing the fault trees, hazard exercises, and then we try to see how the combination of how the functionality of all the alternatives allow us to select which is to be the most suitable alternative for the case of remote pilotage. So we did it, we tested, and then basically we determined actually a process to know how to define this selection. So it's important to know or understand what kind of system is being considered and how complex it is. The purpose of our modeling. So if we create a model for what purpose is going to be used, for supporting the design phases of the technology, or for just for analyzing safety and risk aspects, that's something of both. That's something that we include there. And then, of course, having a heavy consideration of the end users. So who will be using these models and for what purpose will basically support the development of the task on the development of the entire concept. So what we did is kind of like a framework. We utilize it to make these comparisons together with end users on these modeling techniques. We basically can defining a specific modeling technique. The tool that we utilize for this is SysML, which basically allow us to have the diagrams describing the entire components of a remote pilotage and the entire processes for defining how remote pilotage is supposed to work and what are the basically the involvement of specific stakeholders on different parts of the process, and then start to identify how this composition of components in the process will be interacting and what kind of like a behavior we will have on the operation of the systems to understand how the entire remote pilotage operation can be provided and how it's supposed to work in a defined process. So we have different type of diagrams. I'm just showing these two short diagrams where we have the description of components and then the remote pilotage process in the general view. Of course, when you go into the elements that you can see on these models, you will have more details related to requirements, specifications, elements related to the execution of each step on the process for remote pilotage. But I will show you also where you can find those details more, where you can find that information more in details in the specific publications. Then we did our hazard analysis utilizing advanced methods focused on systems engineering approach. So which is this STPA, System Theoretic Process of Analysis, which is basically a new, well, it's not anymore new. We have more than 10 years of hazard analysis technique for complex socio-technical systems, which consider safety as a dynamic control problem rather than just focus on preventing failure. So how to basically put actions among different kind of like components on the system or even roles of particular stakeholders to enforce a kind of like a specific safety performance, and then defining what is going to be like the feedback that you will get to know that the actions that you implement on each part of the system is effectively working. So somehow of confirmation to know that the actions for controlling safety are being efficient and can be basically corroborated by a specific stakeholder or by a specific component in the system. So we made this systemic description for remote pilotage, as you can see it there. Sorry about the picture. I know it's too small and there is a lot of details, but I just wanted to show it that there are details about who are going to be involved in this process of remote pilotage, components and functionality of technical elements for remote pilotage that may be embedded into the entire process, a kind of like a controls, safety controls that will be incorporated, and then the feedback loop that we will have for knowing that. Hopefully having a confirmation that the control is working as such. We analyze all interactions in remote pilotage operations to also identify potential issues or potential unsafe actions, unsafe control actions, as we call it sometimes, to know what are the issues that we may face, and then to later elaborate what we can do about that. So in the hazard analysis, we basically focus on these the 6 specific losses, going from loss of life or injury to people, and loss of damage of on ship and cargo, loss of or damage of external objects, loss of the mission, loss of the environment, affectations to the environment, and then loss of customer satisfaction were basically the main general losses that we evaluate there. We have 5 system-level hazards considered there. So ship violate minimum separation standards en route, ship does not maintain a safe under-keel clearance, ship flips designated route, lack of communication between remote pilotage stakeholders, and then lack of information sharing between remote pilotage stakeholders during the execution of the operation. And then once we basically identify these general level hazards or system level hazards, we went into the task together with end users of the remote pilotage to identify more than 150 unsafe control actions that need to be tackled, and we need to know how this will be controlled. So I just make a short list of some of them that we identified and how they are linked to a specific hazard. So we then combine this kind of like unsafe control, unsafe actions to identify more than 800 unsafe scenarios. So they are causing these unsafe actions that we see. And then we start to analyze it in different categories. So we have more than 50 categories to analyze, or to basically include these unsafe control actions that we detect. Issues related to hardware, issues related to human factors, issues related to incomplete, incorrect, clear, or lack of data. And then once we basically know the categorization and the identification of this unsafe control action, we start to redefine controls to ensure that this unsafe control action can be mitigated, and what kind of like a mitigation strategy will be used for controlling this type of scenarios that we identified there. So, as I say, we evaluate different type of clusters, safety related to the equipment. I'm not going into details here. You can see all the equipment that was included on the evaluation for that. Safety and security related to information exchange. This was very important, especially because the information is transferred from a remote location. So everything what is related to ship dynamic data, fairway traffic info, systems of board, weather info, water depth, and other type of communication that needs to be transferred in the provision of remote pilotage was also evaluated there. Safety related to human factors, so things related to the lack of skills, issues related to fatigue, stress, distraction, lack of trust, language barrier, transmission of message markers was something that we also evaluated there, was also included in this evaluation. Just to show an example how the evaluation goes in these human factors, if we focus on the lack of a skill of competence, we focus on evaluating skills related to remote pilotage, so or the remote pilot, navigation and suggestions, pilotage planning, establishing connections and sending information, suggesting emergency procedures, communication skills, situational awareness and handling of new equipment, among others, were kind of the things that were discussed on this kind of like a lack of skill and competence. The skills related to the master and the navigation crew of the ship that is eligible for this remote pilotage. So better navigation, communication skills, executing emergency procedures, and understanding the kind of like instruction given by remote pilotage. That's something that we basically evaluate there. Some risk control measures for that. So selection of the ship and fairway for knowing where, how, or when this remote pilotage can be basically provided. Simulation practice of remote pilotage, something that people can be tested, getting to know how the service is provided. Experience of skilled pilots on some kind of like a training or preparation needed for that. We're also evaluating as a risk control option. Duplex communication or hard duplex communication was also mentioned there as a kind of like having this kind of like a robust instrumentation for ensuring that the communication is working all the time. And then certification of remote pilotage and its validity, training for remote pilotage, as I say, include emergency procedures and other elements related to how to better understand specific situations and how to react to those. So the kind of like a different type of risk control measures were analyzed there. We basically categorize these risk control measures in the estimation of risk. So we have some 18 subcategories as a low risk, 9 subcategories included as a medium risk, and then 22 subcategories as a high risk levels. So this categorization was actually done before we see the effect on the implementation of risk control measures. So the idea here is that the risk control measures are supposed to reduce the risk. We have some kind of like a initial evaluation about that. So for understanding what is the cost and benefit of benefit in terms of effectiveness of each risk control option, we also made that estimation. So the risk control measures that we determined there are basically categorized on this kind of like a potential they have for reducing the risk or mitigating the risk. As you can see, there are 5 categories there, going from very low effectiveness, where only 2 risk control measures were categorized there. And then the highest is level 5, which is very high effectiveness of the risk control measure, where together with the experts and the entire kind of like stakeholders involved in remote pilotage, we evaluate 164 risk control measures with a very high effectiveness, or effectiveness that can go from 80% to 100 risk reduction. Then we start to evaluate the cost of implementing those risk control options. As you can see there, 53 risk control measures are considered to have no direct cost, and then only 2 risk control measures with the cost above 1 million euros were considered. So the main number of risk control measures were estimated as no direct cost, low cost, And then the other half was split between average cost and high cost. So going to a maximum level of 1 million euros. That's how you can see it there. Then, of course, these risk control options can be separated or can be basically evaluated on the implementation of the cost in an individual way. So then, of course, people are also interested on how effective will be if we combine different risk control options for the application of the different alternatives that we propose, and to see what is the most effective with the less cost implemented there, to try to find configurations which are more suitable for that. So I'm showing this model that we create for evaluating this connection among risk control options, but don't pay attention to the model. I know it looks ugly and difficult to read. So, and we know also that with the stakeholders that, okay, the model works, but it's quite difficult to actually utilize as such. So then what we did is to basically utilize this type of model on creating these kind of like diagrams and this kind of like entire model for the calculation of the most efficient combination to create a specific kind of like interface. So basically nobody likes to see this type of models. That's the purpose of that picture there. Then we create an interface that you don't need to see the model as such, but you have some kind of like a software interacting with the functionality of the model to calculate the combination of this risk control option and to see the effect on the effectiveness of reducing the risk, and then the potential, well, the issue that you are basically tackling with the risk control option and the effectiveness on reducing the risk, and then something related also to the cost of the implementation of those combinations there. So more details about this analysis I will share to you the information on that, but this is kind of like a nice tool that we create. We are trying now to utilize the basis of this tool even to other projects where this kind of like a cost benefit analysis need to be always calculated there. But that's basically something what we do. So conclusions from remote pilotage operation, and in particular in this work that we did for the risk analysis of remote pilotage. So more than 50 lost causal factors were identified on this remote pilotage, and specific risk control actions were determined for that. The risk management strategy defined with the risk control options should be used as a foundation for defining a structured management system to continue the design, because it's not yet ready, and the future operations of remote pilotage. That's something that we are working on new project ideas and applications that we are now developing in Finland. And the output of this work supports the definition of safety requirements. We mentioned it also in the previous presentation of the project, but this particularly in relation to remote pilotage. So preliminary abstract level requirements exist in recently renovated Pilotage Act, but this kind of information can give more detailed instructions or requirements to specify how remote pilotage can be done in a safe manner. We did, in the project, we carry on a demo for remote pilotage in Finland in 2022. And the results of this study were also utilized on demonstrating or basically making the setting for remote pilotage, and then to see, corroborate what kind of issues are also faced still on the actual execution of the remote pilotage as such. For next interactions, the scope of the analysis should be expanded to a higher level. So we want to include more like the views from management and other authorities, maritime authorities, for this entire remote pilotage. So our idea is that now on the plans that we have for continue this remote pilotage work is to extend this risk analysis to the entire umbrella that can be covered and how safety can be controlled if we think about providing the service in the future. So together with FinPilot, we are moving toward the development of a dynamic risk model tool that can be basically utilized at any moment for operational and analysis of operational incident database, to also try to foresee some risk events associated with remote pilotage and actually do action before we can basically face any issue. So more like a proactive approach to control risk and more dynamic. That's kind of like the idea that we have. All the information that we have related to remote pilotage is located in this doctoral thesis. Here is the link, and later when presentation is shared, you can go more into details about elements embedded in this analysis, but I basically recommend you to look into this doctoral thesis because we have all details about our work related to safety assurance and risk analysis for remote pilotage here. So I'm just closing quickly, as I say about the gyroscope, we are working on risks of smart shipping and green strategies. So in gyroscope, we are trying to look into autonomous maritime technologies or solutions that can be incorporated into aspects related to winter navigation. So we have discussed about what kind of technologies will be supported for or can be utilized, for example, to provide assistance to ships operating in ice, or to basically be aligned to the role of, for example, the icebreakers, and a better way that they can actually control what, for example, vessels are doing when navigating in ice conditions. Several kind of like cases can be discussed with them, and some kind of like potential actions to move forward. This collaboration is discussed with some specific stakeholders there. Of course, when we talk about this autonomous shipping in ice conditions, it's totally a different approach. It's more about how those technologies can actually be a good element to enhance the very good work and the advanced work on controlling safety that, for example, icebreakers and all the maritime clustering linked to winter navigation is doing already in Finland. So that's our main purpose. So develop an integrated and optimal framework for analyzing hazards across multiple system configurations. So that's something that we are trying to do. That, for example, if we utilize specific technologies, like, for example, this electronic lookout, or all that type of technologies related to sensors and cameras, how they can be utilized, for example, in the provision of a specific operations on assistance, and then how we can basically elaborate specific indicators in a kind of like a model that control or ensure or analyze risk in a dynamic manner into the potential application that we may have in the future for this project. Aalto, in Aalto, we have this autonomous shipping model for operations in ice. So we're trying also to test to see that how technologies like LIDAR, sensors, and other applications can be good for recognizing ice fields, and to determine, for example, the alternative of the best paths to navigate in ice conditions. That's something that we are basically doing, or how to basically calibrate and support a navigational system that allows an optimal operation, for example, of if a ship is navigating in an ice channel. So this kind of like a testing and evaluation, that's something that we are doing with our models there. So a potential new project is coming if everything goes well on that. So that's something that also we are kind of like heavily collaborating there. And just to close this entire presentation, I'm happy and hope that you are still awake and you find it interesting. So, but in general, we see this safety assurance of smart shipping need to be early in the design phase. So creating technologies and systems that are safe by design, that's quite important. And this is kind of like requires a huge transformation and approach that we utilize in the maritime domain. Then systems complexity and software controlled operation will be increasing. That's something that is embedded in the nature of developing this smart ship concept. So it's important for us, and particularly for people related to research and with scientific foundations, and how we can adapt or create new methodologies to assess risk and determine safety management strategies in a dynamic way. That's kind of like a very important. Human automation, shared control requires an efficient teaming. So as I say, humans will be always in the loop of safety when it comes to smart shipping. So it's either the heavy involvement that they will have and heavy responsibility they will have in the design phase, and then the needed interaction that we will have among these smart systems, and they will be operating together with humans. So that's how it is. So safety requirements, and try to see what is the kind of like changes that we need to specify to justify a similar equivalence of safety on these smart ships compared to the most ships or most advanced ships operating nowadays is quite important to represent. So these requirements are somehow produced on this type of research and are used as a basis for technology approval and applicability to determine operational case and conditions. As I say, we try to determine this kind of like a basis of safety requirements and try to discuss it on venues that, for example, the main people in charge of having these affectations to the regulatory framework can help us on making this, we can help them actually into making the changes necessary to start to see a better and safer introduction of these technologies in the future. As I say, investing heavily in the design phase is a need, but the radical transformation for the industry approach for safety, that's something that is just what it is, and we cannot escape that. So it's a huge compromise that we need to do if we are moving towards having this type of advanced ship concepts in the future. Then, of course, there's the issue of security assurance. Not really my topic, but I'm very happy to collaborate with any expert related to security assurance, cybersecurity purposes. That's something that actually was one of the main purposes for me to be here in Tallinn and collaborate here with Taltech. So security assurance is quite important. So we need to make a definition of data transmission requirements of ships, how we ensure the functionality and the data transmission of sensor, control cameras, and remote maintenance, etc., how this can be executed in an efficient manner and guarantee that our systems are secure at all time. Plan and installation of critical infrastructure such as voice and antennas and other IT systems. How to protect those is also quite important for that. Reliable data links between the autonomous shipping or autonomous maritime technologies or smart shipping concepts and technologies, and remote monitoring and control center. That's something that's quite important. Cybersecurity protocols and practice to avoid losing, altering, and hijacking operational information, or potentially even hijacking the entire autonomous vessels. In autonomous systems, we are already collaborating on these cybersecurity protocols with, for example, with colleagues in Korea and Singapore. So, and as I say, that's something also we are trying to push for on the collaboration here in Taltech. And this is very important, and to know the magnitude of the importance of this type of issues, let's go back in time to remember what happens in 2007, when we have this cyber attack with the NotPetya malware. And this is kind of like a cyber weapon that severely affects Maersk operation, even though it was not targeted to Maersk, but it ends having a huge affectations to Maersk. So these affectations to the systems basically provide having a huge congestion of ports and the delay of cargo. Maersk was forced to rebuild its IT infrastructure in 10 days. And of course, this attack created losses more than 300 million, as well as a reputational damage. So if we think about that in the future, we are talking about smart ships, which are interconnected. So an ugly scenario may be losing the control entirely of this smart shipping concept somehow. But a very catastrophic scenario may be having an affectation of everything what is connected among this type of concepts, including other ships or other critical infrastructure. So this is quite important to understand that this is an issue that we need to work for not allowing to happen. So I finish here. Thank you very much for your assistance to this seminar, and I'm happy to answer any questions you may have.
Osiris, now the floor is open for questions, and Ahmed has raised.
Hello?
We can hear you.
Thank you. Thank you for this presentation. I really liked it, and a lot of information. But about the security assurance, which is the topic that I'm actually working with, I was going to ask the question on how do you secure the communication between during your studies, but apparently this is a thing that you're actually actively looking into.
Yes.
And sorry?
Yeah, go ahead. Sorry.
Yeah, and I was wondering if you can tell me how was it during the data calculation or collection? How was it of cyber from the cybersecurity perspective? How was it hard to secure the communication And as for the AI, did you consider as well the cybersecurity aspect that comes, or vulnerabilities that comes from implementing AI? Most likely, like, let's say, machine learning, or the I would say model poisoning, and the input manipulation when it comes to the I would say, how do you call it, the image recognition or sensory data as well. Yeah, that was my question. All of
Okay,
that.
I will start for the last part, and it's quite easy to answer. For the AI implementation, that's something that was not included on this analysis. We discussed about that, but it's also unclear about what is the role of AI on this kind of like application that we have. So that's something that we were discussing with other partners on analyzing that, but we were mainly looking into this kind of like ensuring this data communication link. And that's something that we did together with the colleagues in a company, which I don't know if I can mention, maybe not, maybe better not to mention. But some of that information is not publicly available because of security matters. But I think you may find something related, at least, to, or some more details related to the data link on this doctoral publication. Maybe some links to that. I know that there are some papers. But I don't know if they are publicly available, and I'm now concerned if I can say something about that, because that's more like a
it's better not, yeah. It's better.
Yes, not, yeah. That's better to maybe let's exchange some emails and let's see if I can provide more details about this to you, because I know there are some things that I could say, but I prefer not to say it.
Yeah. Okay. Thank you very much. And yeah, let's see if we can, I can help out with the data security as well, because this is part of my my PhD. Thank you.
Yeah, this is something for the data security. Something that we are working is, for example, we are utilizing more advanced risk assessment methodology to support this kind of like a cybersecurity risk analysis that we are doing. But the technical composition of the analysis as such always come from experts which are not really in my group. Like, for example, I mentioned the collaboration we have with Singapore and with Korea, because they are the ones with the expertise on the technical elements for cybersecurity. We are mainly helping them on how to establish this suitable process for more advanced ways for controlling these security issues there.
But at least in our department, I think Pentti can also reiterate that we are trying to implement the technical part, and we are working on at least building some kind of solution to work on the monitoring data, sending and receiving, and maybe log processing as well. So yeah, maybe we can, from Taltech side, we can help in that aspect.
Yeah. Yeah, thank you. Yeah, that's one of the main reasons why I'm here.
Thank you.
Thank you. Do we have any other questions?
Yeah, hello, Osiris. I have one question. Thank you for the presentation. I think one topic which is quite often not discussed that thoroughly is the assessment how good the systems on board the vessel actually are. Let's say we know more or less the requirements, that we have to be able to identify the objects, we have to be able to follow the call reg rules, we have to have some certain redundancy and resilience in our system. But let's say the human captains, they have to comply with the requirements, and they have to get their certificates to be able to navigate. And basically from the vessel, you should also have kind of certificate which tells how good you are. We are, Aalto has a spin-off company which has developed 2 autonomous vessels, and we have had to prove to our maritime administration how good the vessels are actually, how well they actually can navigate. And this has been quite a tricky procedure, because there is no real guidelines on that. So do you have any vision on that?
Yeah, and I suppose the challenge goes to really get to know details about, to certify that how well inside the bridge of a vessel everything is, which is kind of like always a challenge because I don't know how many ships will be open to have these discussions and to share this type of data. In this context, we were discussing in Finland at some point about that also from on-site operation, how we can utilize either technologies or approaches to actually define that a ship is operating safely in a specific area. That was mainly important for the issue that we have now in the Gulf of Finland. So we were discussing about how to basically look into the on-site or the actual operation of the ships and make a specific detection of issues that confirms that the ship is operating in a safe manner and is not basically influencing the environment or compromising the safety of maritime traffic in general. But from what you said about inside the bridge and how well the systems on board the ship, this is something that is very interesting, but I understand your point that this is very difficult because of how much availability of data and openness you will have to discuss these issues. I don't know. That's interesting.
Yeah, and there are so many elements. I would say we at Mindship, which is this spin-off company, we are participating in one Horizon Europe project now, where we only aim to certify the server solution, basically only the communication protocol between the vessel and the ship. And already this is so complex task to do this. The idea is that we use AI tools to assess those different server solutions because they might be so different. So it's quite hard to assess them. And the project aims to develop AI-based solution to say whether some certain solution corresponds to some certain standards. So yeah, I think that's interesting and very big field because you basically have to do a driving test for your vessel, and this includes your object detection, your navigational decisions, your communications, your reliability, so a lot of things.
Yes, that's very interesting. Maybe we can do something about that.
Yeah, we could think something. Yeah, would be happy to discuss it in more detail.
Good. Nice to see you, Christian.
Yep, nice to see you.
Do you have any other questions?
Nothing on the chat.
No.
Hello to Ulla also.
Yeah.
Thank you for listening, Ulla.
Ulla is still there, he left.
Yeah. So if there are no more questions online or in the room, then thank you, Osiris, for this presentation. Thank you, everybody, for listening. And we finish here. So thank you and have a